Good morning, ladies and gentlemen. Nice to have you here. And this title is 3D building modeling with multi-source data. And this is a case study from Hong Kong, the high-density, high-rise areas. And I'm Frank, the second one. Currently, I'm a research assistant professor as a faculty of architecture at the University of Hong Kong. And in fact, this is a very intuitive and straightforward method. So let's split this presentation into three parts. First is the background and opportunity. The second one is the method and the pilot study. And the third one is the discussion and future works. Okay, so first let's have a general background about building modeling. Sometimes it's referred as the as-built game, but in this research we didn't see much of the information out from the measurements, so we would like to call it the 3D building modeling instead of as-built in reconstruction. So if we have perfect and ideal building models, then it can be part of the digital foundation of smart city development to enable a lot of applications such as the smart construction, convention, cooperation, house aging, accessibility, energy consumption, reduction, effect, and heritage. And the popular method, you may know, includes a lot of semi-auto methods such as the photogrammetry, the upright photo is an example of the models from photogrammetry. It's a color mostly. And another is a point cloud based. That means we scan all the point cloud as is, but we keep it as the original data, such as it's a bit similar as the music. If we have a very original music, we can decide to whether to proceed into some compressed format such as MP3. But we can also keep the original music on the disk. So this is kind of a point cloud method. And another one is the GIS based method such as the 3D building. So then we still have another rules from architectural and construction practice and regulations. So this is the possible data types. For the photogrammetry, we have the photos and videos. And for the point-cloud based, many point-clouds. And for the GIS, we have different layers. And for the rules, we have the local knowledge. So this problem is not new. Actually, the academia started about 20 years ago, but still it's very challenging, especially in the scenario of city information model. The difficulty here is the unsatisfactory of semantics, or we can call it abstraction, because we got the concept of anything as abstraction, as concept, but in such building modeling methods and results, we don't have a very satisfactory abstraction. The results, the consequence is that we have very huge size of data, such we can about hundreds of megabytes of point clouds, and we have poor usability, and also we have very poor details of models. So the obstacles are mainly on the complexity of the problem, the incomplete data, and noise. Because the data too can be enlarged in the high-rise areas of cities. So this is a general roadmap on how can we do it. So this is the source. We have camera, we have laser scanners, we have the span, and we can produce the image point cloud. And the final output is kind of a semantic rich building models, and we can do the smart city applications. The procedure here is the range of the building modeling. And generally we have two methods. One is model-driven, model field method for research, and another category is the data-driven. I can give an example of our earlier study. We include some image and a library of components. We formulate nonlinear constraint optimization, and we can use the solvers from the OR to automatically build the model. And that's the example of the model driven. For the data driven, that means we rely on our input data, mainly the point clouds. So what about the result? In fact, if we count the number of the data types, we have the single type method and the multiple type method, multiple source method. So for the single type method, as we list here, is averagely the LOD, means the level of details, is around LD2. That means we can have the prismatic blocks and we can have some roof shapes, but no further improvement here. And for the multi-source, still in LD2. And if you add some manual work, it can be LD3 partially. So the opportunity here is that we want more abstraction and semantics, and currently the for-profit models, commercial models, such as the Google Earth, they are not open to us. And the existing method has some flaws, so we would like to recheck and to improve the method of the LD2 in this study. The opportunity here is why we can use multi-source is that we have strong object recognition method for the point clouds that is can be obtained from the data. And in fact, this method can be facilitated by the map, by the digital map. And we still have some a priori rules from our practice of an architectural designs. So this is kind of knowledge. For example, we can have the major elements on the rooftop to be in parallel with the edges of the footprint or the edge of the roof. So let's have the pilot problem. We have 4 square kilometers in the central western district of Hong Kong. There we have over 1,000 blocks of densely distributed buildings, and we have the airborne data here for all the 4 square kilometers with a density of 4 points per square meter, and we have the topographic map here. Now, we also select a few list of few rules about the how the rooftop elements from the reviews and from the observation. The final output is LD2 models in the area, including almost all buildings in the format of the Quadrant. So let's have a close look at the data. In fact, the digital map already contains all the information from the LD1 models, that means the flat roof block prism model. And the later data contains some more details on the rooftop. And they are in the same HK grid systems. And the digital map can export all necessary data in the GeoJSON for our in-house development. And we hard-coded all rules in the program. The process of 5 steps. The first, we want to have this is an example for demonstration. We have a small area of the open view, and we filled all the roof points according to the map. And then we cluster the guiding directions of each building, 1 or 2, or 3 or 4, from the footprints to get the guiding directions. And then we use the ransack to get the planar primitives from the filter point cloud. So this is the result of ransack. The next step is we rectify some of the shapes if it looks weird, because usually we sort the rooftop elements should be in line with the major edges. And then the step 5, we select the primitives to create 3D volumetric shapes. And that is the result of our building. So for the overall results, we developed an in-house plugin based on the top compare and the video available soon. And we ran it on a notebook computer, and the time cost is for over 1,000 buildings, it costs 5 minutes. And the clustering in all the directions is actually very fast. It's less than 1 second. And we do not need any manual pre-processing because the georeferencing was already done by the airplane, GPS, and AMU sensors. So about quality, we also use these small areas. So the top right is we have two different colors. The dark color stands for the LOD web block, and the light color stands for the rooftop elements we find. From the rifles one, we can use the panda parameters to get close to the curve face. And this is a comparison image from Google Earth. So, and the errors, the branch errors, MSE is from 0.06 to 0.2 meters for segmented point. And we think this was accessible since the accuracy of the data itself is around 0.3 to 0.1. All right. We have the pros of this approach. It's very fast and also linear increasing when you apply it to a city scale, because we reduce the size of the point cloud from the tens of millions to thousands based on map. And the error is okay, but we still have some disadvantage. The first one is currently we use the planar parameters, but in the future we can adopt the curves of the spheres and the cones. They're not that difficult, very easily. And the second disadvantage is that currently the airborne data is mainly emphasized on the rooftop. So for the facade, it's all the point is very sparse, and we cannot use that. Maybe it can be completed by some other radar, such as from the SAR and the SLAM or some UAVs. And in this previous study, we have a limit. We mainly validate our results through observation, and so we do not do much of the comparison study there. For future research, one is we can try to advance the LOD models to LOD3 with more type of data and with more knowledge to explore. Another direction is we can do the semantic enrichment for actually smart city applications. For example, we can use the regression models to get the thermal properties like this. We do have. And also we can recognize the AC units, satellite dishes, green areas for the specific management purpose. So let's come to the end of the presentation. References, and thank you for your time. Any questions?